This object is smaller than your hand. It weighs less than a paperback book. And at the height of the AI boom, a single one sold for more than $40,000 when you could get one at all. Because for a while, you couldn't. Companies were placing orders a year in advance. Startups were listing their chip allocations as assets when raising money, the way oil companies list reserves. And in Washington, Beijing, Taipei, and Brussels, governments began rewriting foreign policy over a piece of silicon. Think about that. Not gold, not oil, not weapons, a chip. So here's the question this entire story hinges on. How did a tiny slice of sand, because that's what silicon is, refined sand, become the most fought-over resource on planet Earth? The answer runs through a laser that fires 50,000 times per second, a machine that ships in 3 cargo planes, an island that the global economy quietly depends on, and a gold rush unlike anything since the discovery of oil itself. Welcome to Hidden Value. Before we can understand why the world is fighting over these chips, we need to understand what they actually are. And the easiest way to do that is to imagine an office. Inside your laptop or phone sits a CPU, a central processing unit. Think of it as one extremely intelligent office worker. Brilliant, versatile. It can handle your email, your spreadsheet, your browser, juggling task after task, one after another, at incredible speed. For 50 years, that one brilliant worker was enough. Then a different kind of problem showed up. Imagine you need to color in 1 billion tiny squares. Your genius office worker could do it, one square at a time. It would take forever. What you actually want is not one genius. You want thousands of ordinary workers, each coloring one square, all at the same time. That is a GPU, a graphics processing unit. GPUs were invented for video games because rendering a game means calculating the color of millions of pixels, dozens of times per second. Massively repetitive, massively parallel, perfect for an army of simple workers. And here's the twist that changed history. Training artificial intelligence turned out to be the exact same kind of problem. Not one hard task, but billions of simple ones all at once. Companies then went a step further. Google built the TPU, a tensor processing unit, and others built so-called AI accelerators. If a GPU is an army of general workers, these are armies of specialists, custom-built to do one thing. The specific mathematics of AI, faster and with less power. CPU, one genius. GPU, an army. AI accelerator, an army trained for exactly one war. Simple enough. But this raises the obvious question. Why does AI suddenly need armies of silicon workers at all? In late 2022, a chatbot called ChatGPT reached 100 million users faster than almost any product in history. To most people, it felt like magic appearing out of nowhere. It wasn't magic. It was mathematics, on a scale that's genuinely hard to comprehend. A modern AI model learns by digesting enormous amounts of text, images, and code, adjusting billions of internal dials, called parameters, over and over, trillions of times, until patterns emerge. Every single adjustment is a calculation, and the totals are astronomical. Training one frontier AI model doesn't happen on a computer. It happens on tens of thousands of GPUs, wired together into what is effectively one giant machine, running non-stop for weeks or months. Reports suggested that one leading model was trained on roughly 25,000 high-end GPUs running for about 3 months. Newer systems have used over 100,000. These clusters devour electricity on the scale of small cities. They require networking so fast that the cables connecting the chips become their own engineering discipline. Data centers are now measured not in servers, but in megawatts. And here's the part most people miss. Chatbots are just the visible tip. Image generation, video generation, self-driving cars processing the world in real time, robots learning to walk and grasp, AI systems folding proteins and hunting for new drugs, climate simulations, financial models, and yes, military systems, analyzing satellite imagery and battlefield data. Every single one of these runs on the same underlying fuel, computation. which means demand for these chips isn't a bubble tied to one product. It's the demand of an entire civilization deciding, more or less simultaneously, that it wants intelligence on tap. So the demand is nearly infinite. Now for the uncomfortable part. The supply is not. Let's go back to that $40,000 price tag. Where does it come from? Start with scale, but not the kind you're thinking of. The features on an advanced AI chip are measured in nanometers. A human hair is roughly 80 to 100,000 nanometers wide. The transistors on these chips are built at geometries of just a few nanometers. Structures so small they brush up against the limits of physics itself, where individual atoms start to matter. A flagship AI chip packs on the order of 80 billion transistors, 80 billion microscopic switches, onto a piece of silicon you could hide under a playing card. Newer designs push past 200 billion. Manufacturing at this scale is arguably the most difficult industrial process humans have ever attempted. It takes place in fabs, factories cleaner than hospital operating rooms, where a single invisible dust particle can destroy a chip. Each wafer of silicon passes through hundreds or even thousands of steps over several months. Layer upon layer, etched and deposited with atomic precision. And even then, it often fails. This is the dirty secret of the industry: yield. Not every chip on a wafer works. When a new manufacturing process launches, a significant fraction of chips can come out defective. Every dead chip is money burned. The working chips have to carry the cost of the failures. Then the chip has to be packaged. And modern AI chips aren't one piece of silicon anymore. They're several, stitched together with connections finer than anything else in manufacturing, and fused to stacks of ultra-fast memory called HBM, high bandwidth memory, towers of silicon layered on top of each other like a microscopic skyscraper. This memory alone is so difficult to make that only 3 companies on Earth produce it at scale. Add the interconnects that let thousands of chips talk to each other at blinding speed. Add liquid cooling, because these chips run hot enough to cook on. Add power delivery systems that feed them more electricity than an entire household uses. And beneath all of it, research and development budgets in the tens of billions of dollars spent before a single chip is sold. $40,000 starts to sound almost reasonable. But here's the revelation that stunned even Wall Street when it finally sank in. The company that designs the world's most coveted AI chips doesn't manufacture a single one. Almost nobody does. Nearly all of them are made by one company, on one island, that most people had never heard of. In 1987, a 56-year-old engineer named Morris Chang did something the entire industry considered strange. Chang had spent decades in the American semiconductor business. He understood something nobody else fully appreciated. Chip companies hated building factories. Fabs were brutally expensive, obsolete within years, and demanded relentless reinvestment. So in Taiwan, Chang founded a company with a bizarre business model. We will never design chips. We will never compete with our customers. We will only manufacture for anyone. He called it the Taiwan Semiconductor Manufacturing Company, TSMC. At the time, it seemed like humble contract work. In hindsight, it was one of the most consequential business decisions of the 20th century, because Chang's model unlocked something powerful. Companies could now design chips without owning factories. NVIDIA, Qualcomm, AMD, Apple's chip division. Entire empires were built on this foundation. They dream up the designs. TSMC makes them real. And while its customers competed against each other, TSMC did something quieter. It got better, relentlessly. Decade after decade, it poured everything into one skill: manufacturing smaller, faster, more efficient chips than anyone else on Earth. Today, TSMC produces roughly 90% of the world's most advanced chips. The processor in your iPhone, the GPUs training the world's AI models, the chips in data centers, cars, and fighter jets. One company, one island. Now you might think, surely someone could just build another TSMC. Governments have certainly tried, committing tens of billions of dollars in subsidies. But here's what money can't simply buy: 40 years of accumulated process knowledge. Millions of small lessons about temperatures, chemistries, and timings that exist partly in databases and partly in the instincts of engineers. An ecosystem of thousands of specialized suppliers clustered nearby. A workforce trained for decades. When TSMC builds new fabs abroad, even TSMC struggles to replicate TSMC. This is what economists call a moat, and it created something historians may study for centuries. A small island of 23 million people became one of the most strategically important places on the planet, not because of what's under its soil, but because of what's built on top of it. Some analysts call it Taiwan's Silicon Shield. The theory: the world depends so completely on Taiwanese chips that no major power can afford to see them disrupted. Whether that shield holds is one of the defining geopolitical questions of our era, and every government on Earth knows it. So, nearly infinite demand, supply concentrated on one island. You can probably guess what happened next. In 1848, when gold was discovered in California, people abandoned their lives and raced west. The ones who moved fastest staked the best claims. In the 2020s, the gold rush returned. Except this time, the gold was compute, and the prospectors were the richest companies in human history. OpenAI, backed by Microsoft's billions, needed oceans of GPUs to train each new generation of its models. Google mobilized its own TPU empire while buying GPUs on top. Meta announced plans to amass hundreds of thousands of high-end GPUs, its CEO openly framing compute as the key strategic asset of the decade. Amazon, Oracle, Tesla, xAI, Anthropic. Every serious player began measuring its ambitions in gigawatts and chip counts. New kinds of companies appeared out of nowhere. CoreWeave, once a small crypto mining operation, pivoted to renting out GPUs and became a multi-billion-dollar cloud provider almost overnight. At one point, it even used its NVIDIA chips as collateral for loans. Let that sink in. Banks accepting chips as collateral, like gold bars. Projects were announced with numbers that sounded like typos. Data center campuses budgeted in the hundreds of billions of dollars, with power requirements rivaling entire nations. And through all of it, one brutal fact ruled the industry: there were never enough chips. Delivery queues stretched months, sometimes years. Access to GPUs became a status symbol in Silicon Valley. Startup founders pitched investors not just on their ideas, but on their allocation. Having chips meant you could train models, ship products, attract talent. Not having them meant watching from the sidelines. Scarcity itself became a competitive weapon. If you could lock up supply, your rivals simply couldn't build. Which brings us to the company sitting at the center of this gold rush. Because in every gold rush, the most reliable fortune isn't made by the miners. It's made by whoever sells the shovels. In 1993, 3 engineers founded a company to make graphics chips for video games. They met in a Denny's diner. For decades, that's roughly what NVIDIA remained, a respected gaming brand known to PC enthusiasts and almost nobody else. Then it became, at times, the most valuable company on Earth, worth trillions of dollars, more than entire national stock markets. How does that happen? The lazy answer is, AI needed GPUs. NVIDIA made GPUs. Jackpot. But that misses the real story, and the real story is a masterclass in hidden value. Back in 2006, NVIDIA made a bet that looked almost irresponsible. It spent heavily to build something called CUDA, a software platform that let programmers use gaming chips for general scientific computing. For years, Wall Street saw it as a money pit. Who needed this? Then researchers discovered that neural networks, the technology behind modern AI, ran beautifully on GPUs. And when they went looking for tools, CUDA was already there. Mature, documented, waiting. An entire generation of AI scientists learned their craft on NVIDIA's software. Every framework, every tutorial, every research paper assumed you had NVIDIA hardware. 15+ years of code, careers, and institutional knowledge accumulated on one platform. This is the part most people miss. NVIDIA's true moat was never just silicon. Competitors can, and do, build fast chips. What they can't easily build is a 15-year head start in software, and the millions of developers locked into it. Switching away from NVIDIA doesn't just mean buying different hardware. It means rewriting code, retraining teams, and accepting risk in the middle of an arms race where speed is everything. Economists call it a network effect. NVIDIA's customers might call it a golden cage. Either way, the results were staggering. Profit margins in the 70% range, numbers almost unheard of in hardware, and a demand pipeline so intense that the company's quarterly earnings became global economic events, moving entire stock markets. The gaming company from the Denny's booth had become the arms dealer of the AI age. But even NVIDIA, mighty as it is, controls only one link in the chain. Because here's the next layer of hidden value. No company and no country can build an AI chip alone. Not even close. Follow a single AI chip backward through its life, and you'll take a journey around the planet. The chip is designed in the United States by companies like NVIDIA or AMD, using design software so complex it's an industry of its own, dominated by two American firms, Synopsys and Cadence. Without their tools, designing a modern chip with tens of billions of transistors would be flatly impossible for humans. The silicon wafers themselves, disks of impossibly pure crystal, come largely from Japan, where companies have spent decades perfecting materials so refined that impurities are measured in parts per billion. Japan also supplies critical chemicals and machines from firms like Tokyo Electron. The manufacturing equipment inside the fabs comes from American giants like Applied Materials and Lam Research, machines that deposit and etch layers a few atoms thick. The fabrication happens mostly in Taiwan, at TSMC, with Samsung in South Korea as the main alternative for advanced production. The high-bandwidth memory stacked next to the processor comes overwhelmingly from South Korea, SK Hynix, and Samsung, with America's Micron fighting for its share. Precision optics come from Germany, ground and polished by Zeiss to tolerances no other company on Earth can match. And China sits inside this web too, as a massive market, a hub for assembly and testing, and a key source of raw materials like gallium and germanium, which it has already restricted in trade disputes. One chip, dozens of countries, thousands of companies, each one a potential bottleneck. Remove any single link, the Dutch machines, the Japanese chemicals, the Korean memory, the Taiwanese fabs, and the entire chain seizes up. Notice something. I said the Dutch machines, because the most extreme bottleneck of all, the single most irreplaceable object in this entire global web, sits in a quiet town in the Netherlands, and it might be the most complicated machine human beings have ever built. In the town of Veldhoven in the Netherlands, a company called ASML builds a machine that sounds like science fiction, except every word of what you're about to hear is true. To print features just a few nanometers wide, you need light with an extraordinarily short wavelength, a kind of light called extreme ultraviolet, or EUV. And here's the problem. Nature doesn't hand this light to you. It's absorbed by air. It's absorbed by glass lenses. It barely wants to exist at all. So ASML's engineers had to create it from scratch. Here's how. Inside the machine, molten droplets of tin, each about the width of a human hair's fraction, are fired through a vacuum chamber, 50,000 droplets every second. Each droplet is struck mid-flight by pulses from one of the most powerful industrial lasers ever made. First, a gentle pulse to flatten the droplet, then a devastating one that vaporizes it into plasma several times hotter than the surface of the sun. That explosion, repeated 50,000 times per second, hour after hour, emits a flicker of the precious EUV light. Because glass would absorb it, that light can't pass through lenses. So it's bounced across a series of mirrors, the smoothest objects humans have ever manufactured. If one of these mirrors were scaled up to the size of a country, its largest imperfection would be smaller than a millimeter. The light finally strikes a silicon wafer moving with such precision that the machine's positioning is accurate to fractions of a nanometer, while the stages inside accelerate harder than a fighter jet. Each of these machines contains over 100,000 components. It ships to customers in dozens of freight containers, filling multiple cargo planes. And the price tag runs into the hundreds of millions of dollars per machine, the newest generation costing more than a Boeing 747. Now, here's the sentence that keeps national security officials awake at night. Only one company in the world can build this machine. Not one country, one company. ASML has no competitor, not because others aren't allowed to try, but because replicating it would take decades and a supplier network spanning thousands of firms. When the United States wanted to slow China's AI progress, one of its most powerful moves wasn't sanctioning chips at all. It was working with the Dutch government to restrict the export of these machines. A single company in a quiet Dutch town holding a choke point over the future of artificial intelligence. That's when you start to realize what these chips have actually become. Not products, ration. Every era of human history has had a defining resource, the thing that determined which nations rose and which fell. The Industrial Revolution ran on coal. Whoever had coal had steam, steel, and railways. The 20th century ran on oil. Wars were fought over it. Alliances were built around it. Entire deserts became the most contested real estate on Earth. The Internet era ran on data, the new raw material harvested by the billions of clicks. But data, on its own, is inert. A mountain of information does nothing until you can process it, learn from it, turn it into intelligence. That takes compute. And this is the quiet realization now reshaping global politics. In the AI era, computing power itself is becoming a strategic resource, like coal, like oil, except with one crucial difference. Oil is distributed by geological luck. Compute is distributed by industrial capability. You can't drill for it. You have to build it through the most complex supply chain ever assembled. Governments have understood. The United States passed the CHIPS Act, committing over $50 billion to bring manufacturing home. Europe, Japan, India, and the Gulf states launched their own multi-billion-dollar programs. Nations now speak openly of sovereign AI, the idea that a country without its own compute is a country dependent on others for its future intelligence. And export controls on advanced chips have become a first-line instrument of foreign policy. Trade rules wielded like embargoes once were. The logic is simple and a little chilling. If AI becomes as transformative as electricity, then whoever controls the chips controls the pace of everyone else's future. Which raises a question with trillions of dollars riding on it. What happens if the supply breaks? We've actually seen a preview of what a chip shortage does to the world, and it didn't even involve AI. Between 2020 and 2022, pandemic disruptions choked the supply of ordinary, everyday chips. The result? Car factories on multiple continents went silent, not for lack of steel or workers, but for lack of a few dollars worth of semiconductors. The auto industry alone lost hundreds of billions in revenue. Prices of used cars, spiked worldwide. That was a shortage of simple chips. Now imagine the same fragility applied to the most advanced chips on Earth, the kind produced in exactly one place, on machines made by exactly one company. And the pressure is building from every direction at once. Demand keeps compounding as every industry races to adopt AI. But the constraints are stacking up. Electricity, first of all. Data centers already consume a meaningful slice of global power, and AI is multiplying that appetite. In some regions, the limiting factor for new AI infrastructure isn't chips anymore. It's finding a power grid that can feed them. Tech companies are now signing deals for dedicated power plants. Even nuclear reactors are being revived to feed data centers. Water, used in enormous quantities both to manufacture chips and to cool the facilities that run them, a growing tension in drought-prone regions. People. Building and running fabs requires tens of thousands of highly specialized engineers, and there simply aren't enough of them. New fabs in the West have been delayed partly because the workforce doesn't exist yet. Manufacturing bottlenecks, advanced packaging, and high-bandwidth memory have repeatedly been the choke point, with capacity sold out years in advance. And looming over everything, geopolitics. Export controls tightening, trade retaliation over raw materials, and the ever-present question of Taiwan, where a single crisis, military, political, or even a severe earthquake, could freeze the supply of advanced chips for the entire planet. Here's the truly sobering part. A disruption wouldn't just slow down chatbots. Modern cars contain thousands of chips, so do hospitals, power grids, phones, planes, and payment systems. The semiconductor supply chain has become civilization's central nervous system. We built the modern world on top of a miracle, and the miracle has single points of failure. So why does everyone keep racing forward anyway? Why the trillion-dollar bets, the national strategies, the desperate scramble? Because of what's coming next. Everything you've seen so far, the chatbots, the image generators, is the early chapter. The real reason companies and nations are pouring trillions into compute is what these chips make possible next. Humanoid robots are moving from research labs toward factory floors, learning physical tasks the way chatbots learned language, by training on massive compute. Autonomous factories that reconfigure themselves. Self-driving fleets that could reshape how cities move. In medicine, AI systems are already designing drug candidates and decoding the machinery of proteins. Work that once took years, now compressed into months. Every step forward is, at its core, a compute problem. In science, researchers talk about AI scientists, systems that generate hypotheses, run simulations, and design experiments around the clock. In education, personal tutors for every child on Earth. In space exploration, autonomous systems operating too far away for human control. And in defense, a quieter, more unsettling race. Nations building AI for surveillance, cyber operations, and autonomous systems, convinced that falling behind is not an option. Notice the pattern. In every single field, the pace of progress increasingly depends on one input: how much computation you can throw at the problem. More chips means faster drug discovery, faster robotics, faster science, faster everything. That's the real stake behind the AI chip wars. Not gadgets, speed. The speed of the future itself. For most of human history, we've known exactly what a valuable resource looks like. Gold, heavy, gleaming, hoarded in vaults. Oil, black, liquid power pumped from beneath deserts and oceans. Land, the oldest treasure of all, fought over since the first borders were drawn. Empires rose and fell chasing these things. Maps were redrawn for them. But the most valuable resource of the 21st century doesn't gleam. You could hold it in your palm and feel almost nothing. It's a wafer-thin slice of processed sand, carrying tens of billions of switches too small to see. The product of the longest, most delicate, most improbable supply chain our species has ever constructed. 50 years ago, national power was measured in barrels per day and warheads. Today, a new metric is quietly joining them: how much computation a nation commands. The next superpower may not be the one that controls the most territory. It may be the one that controls the most compute. And that transformation happened silently, while the world was watching other things, inside machines that fire lasers at falling droplets of tin, in clean rooms on a small island in the Pacific, in the minds of engineers building at the very edge of physics. So the next time you hear about another AI breakthrough, another model, another robot, another discovery, remember where it all begins. with a chip small enough to fit in the palm of your hand, yet powerful enough to reshape the future of humanity. Hidden value is everywhere. You just have to know where to look.